In the first chapter of my previous DVD, I went over how to achieve normal mapping. And that's what we've got right here. We've got a flat surface with a normal map on it that gives the illusion that the surface has more surface detail than it actually does. And what I like to do in the first chapter of this DVD is go over an extension to normal mapping called offset mapping, which actually gives the surface depth. Instead of just defining shape, or affecting the normals, it also affects the height. So we get depth added. Just to start off my explanation, what I'm going to do is give you a demonstration of what the end result is like when you add offset mapping to your shader. So here in my material panel, I've got this new property called offset height. And right now you can see that it's set to 0. So I'm getting no additional height added to my effect. Well, let's see what happens if we move this value up. Now watch over here as I change this value here. And what you'll see is that I'm adding this depth to the map. And you can especially see it if I zoom in here and move around. Now it really looks like those cobblestones are popping off the surface. They have actual depth to them. Let's turn it back off again. You can see that when I turn it off, it goes flat. But then as I raise it up, and I'll even raise it up a little bit further this time, kind of accentuate the effect, you can see that the offset mapping is really bumping those cobblestones off the surface. So let's go over how this is achieved. What we're doing here is a really elaborate fake. Because just like with normal mapping, there's no extra detail in the geometry at all. This is all being done with the textures and with the shader. The thing that gives this illusion is the fact that, let's zoom in here, just on these couple of cobblestones here. The thing that gives this illusion is the fact that the pixels that are higher, the ones that are on the tops of the cobblestones, are moving at a slightly different rate than the ones that are the lowest, like down here on the ground or the cement part. And the way that that's achieved is by editing the UV coordinates per pixel. So if we know how high off the surface this part is versus this part, and we know where our camera vector or our eye vector is in relation to the surface, what we can do is shift our UV coordinates around differently for parts of the object that are high versus parts of the object that are low. Now there is one case where this effect breaks down, and I want to show you what that looks like. So I'm going to turn this up kind of high so that you can see this. Can you see how the effect is pulling apart right here, or smearing? That's what happens when you have very strong differences in height. So in these particular areas, there's a high contrast between high objects and low objects, and so you get this texture smearing. And that's why I like to keep this height value at around 0.04. Now, before we get into the shader code, I want to give a quick demonstration of the requirements for offset mapping. The first thing that you need is a height map. And a height map is a black and white image. I'll pull up Photoshop here just to show you what that looks like. It's a black and white image that defines the areas that are high, that are white, and the areas that are low, that are black. And there are a couple of different methods you can use for generating these. What I've done is I've put this in the alpha channel of my normal map. Here's my normal map's RGB, so you can see my cobblestone shapes here. Then if I switch over to the alpha channel, you can see that I've defined each cobblestone as a lighter color, and then the background cement or grout as the darker color. So this is the height map. And like I said, there's a couple of different ways to make these. You could paint this yourself in Photoshop if you wanted to, but actually what I've done to create my height map is, well, first of all, to create my normal map, I actually modeled these cobblestones in high-res geometry. So you can see there's lots of polygons here, and I modeled each cobblestone so that I have this high-res geometry. And I've set up a camera up here in my scene so that it points down and looks straight at my cobblestones that I modeled. So if I take a look here from my camera view, you can see if I render this view here, that's how I got my normal map. And the other thing that I've done, if we go in here to the render window, if we take a look at render elements, I picked elements active, and then I hit add, and I picked Z depth. And what that's going to do, in addition to the regular map that it renders, it's also going to render a Z depth image. Now, if we come down here to the settings, I had to set Z min and Z max. And what this is it figures out what is my minimum depth and my maximum depth. The minimum depth is the distance from the camera at which the depth pixels will be white, and the maximum depth is the distance from the camera at which the depth pixels will be black. So I got out the tape measure in 3ds Max, and I ran it from the camera position down to the surface position, and I measured the distance from my highest cobblestone, and I put that in as my Z min, and then I measured the distance down to the cement area, and I put that in as my Z max. So then when I hit render, it's going to give me an image that is a height map. So that's how I generated mine. And then the other thing you'll notice is that this one is kind of blurry. I found that when you blur the height map, it gets rid of rough or hard edges. So if you look at my normal map, you can see that there's some pretty high contrast or hard edges here between the edges of the cobblestones and the background. And I learned that if you have those hard edges in there, your offset mapping results aren't quite as nice. So I went ahead and blurred out my height map so that there's a really soft transition between the highs and the lows. All right, so that's a quick coverage of generating height maps. Now let's jump into the code itself. The first thing that I want to do is come over here to Max, and I have a shader with the DVD3 Chapter 1 Start shader applied to it. And I'm going to assign that to my scene because that's the one we're going to be working with here in Effects Composer. So you notice when I apply that, the offset mapping goes away, and this is a good place to start. So I'll come over here to our shader, and the first thing that I want to do is add in my UI control. I need to add a spinner that will allow us to control how high we want the height map effect or the offset mapping effect to go. So I'm going to copy this glossiness control because it's already a spinner UI element, and I'm going to paste it, and instead of calling it glossiness, we're going to call it offset height. And it's a slider. We're going to set the minimum value to -1 and the maximum value to 1. And we probably won't ever go that high, but we'll just set it at that anyway. We're going to set the UI step to 0.01, and we're going to name our UI element offset height. And then we're going to set it to that default value that I thought looked pretty good of 0.04. So there's our UI element. Go ahead and save this and update it over here in Max. Nothing changed, obviously, because all I've done is add this UI element. All right. The next thing that we need to do is calculate our I vector. So let's come down here to the vertex shader. We've already got an I vector, but the problem with this one is that it's in world space. And if we look at our surface, our height map on our surface, or the height off of the surface, is actually in tangent space. So when we use the height map that's in tangent space, so I'm going to come up here to our output struct, and I'm going to add a new element to this struct. This is going to be called T underscore IVEC because it's our tangent space I vector, and we're going to be passing it out using text chord 6. All right, so now we need to figure out how to populate that. And constructing a vector in tangent space is a little bit different than making one in world space. We know that we have our I vector, or our eye or camera position here in world space, and we actually need to transform it into tangent space. And in order to make that happen, I need to multiply it by a matrix. So you'll notice that here I'm multiplying my object space position by this matrix to get it into this flip space. So that's what, when you want to transform a vector from one space to another, you have to do a matrix multiplication. And generally, you're provided with the matrices that you need. So here's world view projection, world inverse transpose, view inverse, world, etc. But in this case, in order to transform it into tangent space, we don't have the matrix that we need. We actually need to build it in the shader itself. So I'm going to go ahead and do that right here. And I just have this code already, so I'm going to paste it in. I'm going to call my matrix. So a matrix is a 3x3 grid of numbers, basically, and I'm going to call it object to tangent space transform. The first row of my matrix is the binormal that I'm bringing in. So here's my incoming struct. I'm bringing in binormal, normal, and tangent. So the first row is the binormal. The second row is the negative tangent, and the third row is the normal. The next thing that I need to do is transform my I vector into object space, or my I position rather. So I'm going to call this ob space IPOS, and I'm going to get it into object space by multiplying it by the world inverse matrix. And I want to multiply my camera position here. So there, I've put my camera position into object space. Now from object space, I can further transform it into tangent space. So I'm going to say, or rather, what I'm going to do now is create the I vector. I have my I position, and I need to create a vector. So I'm going to subtract this object space I position from the vertex position. So I'm going to say object space I vector equals object space I position dot xyz minus in dot position dot xyz. Okay, so there's my object space I position, my object space I vector, and now that I have the vector, I can transform that into tangent space. So I'm going to say out. Now I'm filling in this element of my output struct. Out dot TIVEC equals, and I'll multiply my object space I vector by the matrix that I created here. So this matrix is transforming my object space vector into tangent space. There you go. I've created the tangent space I vector, And remember, I need this eye vector in my vertex shader so I can combine it with the height map that I created to create that offset effect. And we're going to offset the UV coordinates per pixel so that they shift what's happening on the surface. So let's jump into our pixel shader here. And what we need to do is come up with a new set of UV coordinates. Right now we're using uh, our incoming UV coordinates, and these are static coordinates. They don't move around at all. And we're going to make a new set of coordinates that move with regards to the height map and the eye vector. And really, I only need the x and y elements of the eye vector. So I'm going to say float 2 t eye vec equals in dot t eye vec. And I want to normalize this because this vector isn't normalized yet. So I'm going to say normalize in dot t eye vec. And I only want the first two components of this vector. So I'm going to say x, y. Now, because max is a little bit different, it uses negative y instead of positive y. I need to flip the y component. So I'm going to say t eye vec dot y equals negative t eye vec dot y. So I'm going to negate the y component there because max uses the negative y instead of positive y. So now I have the eye vector, or the tangent space eye vector that I can use in the pixel shader. The next thing that I need to do is grab my height map from my normal map. So I'm going to say float height alpha equals text 2D to look up into my texture map. And I'm going to use the normal map sampler. This is the same texture that I'm using down here for my normal map. And I'm going to use my incoming texture coordinates for this one. I'm looking up my normal map with my texture coordinates. And I'm just going to grab the alpha channel. So I'm going to say dot A. So this normally gets a float 4, but because I added this dot A on the end, it's only getting the alpha channel. Now, this value goes from 0 to 1. But what I want to do is expand it out so it goes from negative 1 to 1. So I'm going to say times 2 minus 1 for my height map value. And now we're getting down to the really useful part. What I'm going to do here is generate my new hex chords. And I'm going to take my height alpha and I'm going to multiply that by the eye vector, the tangent space eye vector that I've created here. And I'm also going to multiply that by the new UI element that I added, the offset height, that I can control the amount of the effect. And all of this combined together is the amount of offset that I need. And it's varying depending on the eye vector because I've added it in here. And I'm going to take that value, I'm going to add it to my incoming texture coordinates in textcore.xy. And that is going to give me a new set of texture coordinates. Now I'm going to use these texture coordinates to look up my color texture, my specular texture, and my normal map. So I've generated a new set of texture coordinates, and now I'm using that new set of texture coordinates to look up my color, specular, and normal maps. Let's hit save here. And it's telling me that there's an undeclared identifier, world eye, which means I don't have the world eye matrix in my shader yet. I need to come up here to this header and add a new incoming matrix. And we're going to call this one world eye. And I'm just going to copy this line here and paste it And for the semantic binding, I'm going to call it world inverse. So this is going to bring in the world inverse matrix. Hit save, and it updates again. Oh, here's another error. And it looks like I forgot to add a semicolon to the end of this line. Common mistake. Hit save, updates, and now I've got offset mapping. So just like I showed at the beginning, I can control the height here, and I can make it flat, or I can go the other way, set it to 0, get what regular normal mapping gives you, or if you set it like I like it at 0.04, get this really nice parallax effect. Makes those cobblestones just bump off the surface. Now this is a relatively cheap effect, and you can add it to all kinds of things to get really beautiful results. But remember, it does have those side effects of kind of smearing around the edges, and also obviously if you look at your object from the side, there's no actual silhouette here. To get a real silhouette, you have to do something much more complex. But in this case, it ends up being a pretty nice illusion of additional surface detail that's not really there, and going beyond what normal mapping can do to give you some really nice definition to this shape of your surface. So that's offset mapping. I hope you enjoy that and that you can add that to lots of your shaders. In the next chapter, we're going to talk about another cool effect that you can add to your surface to add some interesting surface properties. We're going to talk about reflection mapping.